Okay. First of all, we have to create a new model. Do you have SAP with you? Some of you have SAP. How many? A lot of, perfect. So I will go very slow so you can follow me in real time, okay? New model. Select the unity. Pay attention because SAP has the unity, so you have to select always the unities. You will see the unities here, and you will see the unities here. Pay attention that is not always this situation, because like in Abacus, if you are using Abacus, you don't have unities. You have to pay attention to do everything that is correct, because it's unitless. In SAP you have unity, and generally in the software used only for civil engineering or for not so complicated analysis, you have the unities. We can select Newton and millimeters. And I'm going to select grid only because I'm not interested in this sub option. I want to create my model alone. This part is not important because we will modify the grid directly on the SAP according to our model. So you can select OK without pay attention on these tasks. This is the grid. In SAP you can work only by selecting the point on the grid. So when you have to create a very complex model, you must create a very complex grid. If you click with the right click on the screen, you will see this menu, edit grid data, and modify. We can create also a new, but we can modify. It's better to modify this one. I want to create a grid in the X zeta plane. So I will work only on the plane of the blackboard. So my axes are zeta and X. I don't need anything in Y direction, so we can delete. The length of the beam is 4 meters, so we can create, for example, I don't know, 4 points, each point, each 1 meter. In the zeta direction, we don't have anything because it's a simple beam, but we want to create only a point that is 1 meter. This is the final view of your grid. Okay? Now we have to define the material. So, define, and you have materials, of course. We can create a new material. And you can select everything you want. We can select Italy, steel, the NTC 2008. If you have the new 2018, is okay. And the grade of steel. If we look at the material properties, we have the weight, we have the module of the elasticity, and the Poisson ratio. Then we have also some other properties like the thermal expansion coefficient and the value of the yielding and the ultimate stresses. Yes? Edit grid data. Okay? Now it's not important the yielding and the ultimate stresses properties, because we are performing only linear elastic analysis. So here you cannot take into consideration these values, because for the linear elastic analysis, the software will not consider these values. The only values that will influence your analysis are the elastic values and the Poisson ratio, and so on. So check to have these values of the elastic modulus, that is the one that I told you before, and 0.3 for the Poisson ratio. We can also delete the other materials, because we will not use. Metti 0.3, sì sì.
Lo facciamo noi il materiale. Ma quello lì è standard oppure la
Questo è standard. Usually for the steel it's 0.3. Are you okay with the material?
Can you show again the material properties?
Yeah. Are you okay with the grid? It's a really simple grid. Material property, the important thing is that you have Young modulus you have to look only on the Young modulus and on the Poisson ratio. The other values are not important for the linear elastic analysis. Okay, I can define the cross section. You have the section properties, and I want to define a frame cross section. The other one are for the truss elements that can resist only in tension when you use cable. Area and solid are for the shell and for the brick element. I want to create a beam element, so I want to select frame section. Frame section for the beam element, okay? In SAP you have a library on which you can select a lot of cross section, so we can import new properties, a double T properties. If you have this kind of list, you have to select Euro, because are the European cross section. You can see that you have a lot of type. You have Chinese, you have American. These are the list of the cross section for each country. When you select Euro, we can look for the IPE. Is this one, IPE 400. So the first thing, when you selected the new cross-section, check always the properties. So don't forget to check the properties. Because, okay, for the IPE and H and this kind of cross-section, the properties are always more or less right in the software. But when you have L cross-section or C cross-section, maybe you can have different value for the torsional inertia and for the warping inertia. So you have to know what is the value that you want to use, if they are right or not. Because if you see that something is wrong, you can modify with set modifiers the properties. If you put, for example, 1.2 in the torsional constant, the torsional constant in SAP will be multiplied by 1.2. Is a linear relationship between this modifier and the properties. So first of all, you have to check the properties and give OK if everything is OK. When you create a new cross-section, you have to assign always the material. So if you are using Strauss or SAP or Midas or I don't know, you have to associate the material to the cross-section. This is the one that I have created before, and this is the cross-section. Okay? Yeah. I'm going to write the properties on the blackboard. These are millimeters. I'm interested only on the second moment of area. I will take the greater one because I will design the cross-section in this way, with this flexural axis. So the moment of inertia is 2.32. So we know everything because we have the force that is 5 kilonewton, 5,000 Newton. The length is 4 meters, so 4,000 millimeters. We know the second moment of area from the properties, and we know the elastic property of the material, so we know the displacement that we want to obtain. I can calculate it. I expected from the analysis 2.189 millimeters. Pay attention that in your real life, engineering life, when you have a results, you don't have to be really exact. You don't need 2.189. This can be 2.2 or 2.5 also, more or less. But when you are validating a software, you want to have this exactly value because it's a mathematical procedure. So I want 2.189 and not 2.17. Okay? Because I'm validating a software. I know that finite element procedure is an approximated procedure. So I want to understand how many finite elements I need to obtain these results. And what is the error if I'm using only one element? Okay? In this special case, I expect that with one element, I must obtain the exactly results. Because of the shaped function are on the same grade of the solution. So I must obtain the exact value with my finite element software, on this case, with one element. I don't need to refine the mesh. This is what I expected. Okay, we can create the mesh. Now we have the property, we have the cross-section. In SAP you have to draw. As I told you, the beam element in SAP are the frame, so we can draw a frame. You can use the command draw, or on the left you have the design of the frame, this one, draw frame. You can see that you have a list of properties, straight frame, you can draw also curved frame. You have to select, of course, the cross-section. This is if you want to create releases, so if you want a trussed element with a pinned connection on the end. But we want everything continuous, and of course. I'm going to select the first point and the last point to have a 4-meter beam. This is one finite element beam from the 0 to 4. We don't have anything in the middle. So now the boundary condition. If you want to look on the local axis, you have on the right this symbol, display options. You can display local axis. This is important because local axis give you the orientation of your cross-section. Because cross-section have axis 3 and 2, and the beam axis is the axis 1. The red one is the axis 1.
Always?
In the SAP, yes. In the SAP is always the axis 1 is the red one. In the other software depends on the convention. Pay attention because depends on the way on which you design the frame. Because I designed it from the left to the right, and the axis 1 has this direction, from the left to the right. If you do the opposite, from the right to the left, also the red axis will change. From the right to the left, no, it's not changing. If you look to the extrude visual, you can see that the orientation of the beam is with the strong axis in the same direction that I wanted. For see the extrude visual, again the set display option and general options. You have the standard visual. These are for the color. You have the extrude visual or standard visual that is with the straight line. Of course, you can rotate also the axis, the local axis. If you select the beam, and going to assign, you have a lot of lists, and you have also local axis. With this option, you can rotate the local axis and rotate also the beam, of course. Okay, I'm going to assign the boundary condition. So we want to create a fixed end. So if you're going to assign joint, you can see a list. We are interested in the external restraints. I want to fix everything. You can select by hand everything, or you can use this command that is a symbol of a fixed end. You have to select the point and apply. SAP is really useful because you can see the symbol associated with the boundary conditions. When you change something, you will have a different symbol. So you can understand directly by looking at the symbol. Now the beam is fixed on one end. We have to define the loads. In SAP, you have to define the load patterns, first of all. So if you're going to define load patterns, we can create a new patterns that is force. Okay, now this is very important because if you leave here the number 1, SAP will automatically consider the self-weight of the beam. But now we are not interested on the self-weight, so we have to put here 0. You can see that if you select type of load that is the dead load, you have directly 1. If you select live load, you have 0. So you can select modify. This is the new load patterns. Force, live load with 0. So without self-weight. So now we have the load patterns. We can create the load. Again, assign, not joint now, but joint loads and forces. You can see that you have all the forces and moment. Select the node, the other node, not the fixed one, of course. Pay attention on these three options. You can add the load to an existing load. You can replace or you can delete everything on this node. I have selected this node. Now we don't have anything, so if we select add or replace, the result is the same. Okay, the force is minus in the zeta direction, 5,000 because we have Newton. New SAP version is really user-friendly because you can see directly on the screen the unities. In the other versions, you don't have the unities here, but you have only the unities here. You can also do operation on this window, like 1000 plus minus 4000, and it calculates automatically the value. So you will see the force on the node by if you push apply. So now we have the beam, the boundary condition, the loads and the restraints. We have to create the cases, the linear static analysis. And you can go on define, load cases. We can delete everything because we are not interested in this analysis. New load cases. You can see that we have a lot of type of analysis. We have the static one, the modal, the response spectrum, the time history. Now we are interested only on the linear static. So static analysis and linear. You have to create a name, for example, case 1. And select the load pattern. You can have a lot of load name like force or a lot of load pattern, and the scale factor. So if you want to put the forces equal to 1 and to put 5,000 here, it's the same because the scale factor will multiply linearly the value of the load name. So now we have 5,000 on the force, and then I'm going to put 1 here. But the final result is the same if you put 1 to the force and 5,000 here. It's a linear multiplication. Okay, now we have everything. You have to save the file with the save as. To run the analysis, you have to put this play button, or F5 is the same. When you have a lot of combination, you will see here a lot of load cases and combination, and you can decide if run or not run the combination. So you are not obliged to run everything. If you put run now, SAP will resolve your problem. Now, of course, it's really fast because it's a really simple case. To see the bending moment, you can see on this type of button show forces frame cables, or you can push F8. You can see that you have axial forces and all the forces, internal forces, shear moments. I expected the bending moment equal to 20 kilonewton meter because it's 5 multiplied by 4. This is the distribution of the bending moment, and this is 20. Apply. I'm going to put kilonewton meter. And you can see, if you go on the beam, you can see the values. To see exactly the values, you can do right click on the beam and you will have this type of option. You can see that the shear force is constant, equal to 5, and the bending moment is exactly the one that I expected. We can look at the displacements. For the displacement, you can choose this button, the one near to the previous one, or you can push F6. So you can do everything you want on the deformed shape. You can do the deformed shape if you are performing nonlinear analysis step by step. So you can see, for example, in the pushover, each step of the deformed shape of your frame. You can also amplify the deformed shape by a number that you want, and so on. You have a lot of options, are not important. By apply, you can see the deformed shape that is similar to this one. We can look at the value. I expected 2.189 and I obtained 2.268. I'm not happy with this result. What happened in your opinion? Why is not equal to the theoretical one? Exactly. We have in SAP a Timoshenko formulation beam, so we have also the shear deformation inside. I didn't calculate the shear deformation on this exercise. So I have to add the contribution of the shear. I can call this the displacement of Eulero-Bernoulli theory. So the total one is the displacement of the Eulero-Bernoulli plus the displacement due to the shear deformation. We know all the values because this is the shear, the forces. This is the length. This is the value related to the Young modulus and the Poisson ratio. And I can see this value from the properties. Is the shear area in the IPE, the shear area, you know that is this value. So we have all the values, we can calculate the displacement. Is 2.25. So it becomes closer to the one that I have obtained by SAP. If we want to exclude the shear deformation from the SAP in the SAP and obtain exactly the Eulero-Bernoulli displacement, we can modify the properties. So we can choose to modify the property by the set modifier, and we can increase manually the shear area. Because if I put a very great number, I will put this to 0. You can see that the value is changed. Why is not exactly? One moment. The value is 2.196. This is with the Timoshenko theory. This is Eulero-Bernoulli theory. Pay attention that shorter is the beam and greater is the influence of the shear deformation. Okay? Cioè, se siamo riusciti... We have a little difference because I approximate the value of the second moment of area. I use at 2.32, but the real value is 2.318. So if you use the real value 2.318, you will have the exactly match with the sub values. Okay, was a really simple example. Of course, if you increase 10 times the force, you will increase 10 times the displacement. Because it's a linear relationship. Okay, we can try to create a frame, a more complex frame, not a simple beam like this one. Everyone resolved the beam? Someone have some problems? Perfect. Okay, delete the beam or create a new file. First of all, right-click on the grid data, and we are going to modify the grid. We are going to create this frame. We can put our IPE here. And for example, for the column, we can use an IH column, 280. The dimensions can be like 3 meters. And 3.5, I don't know. Pay attention, if you want to validate this frame, the results with the displacement methods, take in mind that you don't have actual deformability. If you are considered a fixed joint frame. So the only movement is the rotation of this joint. Will be something like this. more or less. You know, the displacement method is the one that you have to resolve the substructure 0 with the fixed joints and the loads. You know the displacement method, right? You did the theory of structures, all of you. Okay, I don't want to spend time to record. So we can create the grid in the x direction. I can split the 3 meters into different values. And in the zeta direction, I create a grid with this dimension, and I split the beam into 2 points, the grid into middle point. We have to define the new cross section, the H cross section. Frame sections. Again, import new property. And we are looking for the H280B. Again, check the properties. And we have to modify the area, cross-sectional area, and the shear area. This for not considering the shear deformation and to consider the actual inextensibility of the beam. Pay attention to the material that is the same of the previous cross-section. Okay. Now we have the IPE and the HAB. I'm going to design the frame starting from the HEB. I'm going to use also the middle point of the grid. I understand. Okay. This is the frame. Again, if you want to rotate the column, for example, you just have to select the column and assign a frame local axis rotation. If I put 90 degree, you can see that I have rotated the column in the other direction. From the local axis point of view, frames local axis, you can see axis 2 and 3, the blue and the green one. If I put 90, are in this direction. If I put 0, they rotate, they will rotate. Okay?
Avete disegnato una trave, non due pezzi di trave, una trave continua, una differenza di così come si fa a notare poi.
Okay, I'm going to repeat the local axis because if you see on the top menu, if you look at the top menu, you have set display options. In this display option, you have local axis for the frames in this menu. If you want to see the extrude version visual, in some version you have this new tab, general option with the extrude. In other version of SAP you have extrude directly in the first one. You can see also the elements that are not connected but interrupted. This is only a visual. It's not the real behavior. It's only a visualization. I'm going to select and put the boundary condition. So I want two fixed points, this one and this one. Again, assign joint restraints and fixed. You can see that the symbols are the same that the previous one. The new thing with respect to the previous exercise is to assign the distributed load. So you can select the beam element of the IPE. We have frame loads, not the joint loads. And you can see distributed. Again, we have the menu with the add, replace, or delete. You can create a uniform load or a different type of load that can be trapezoidal load that is different with the distance along the beam. Pay attention on the direction that can be with respect to the gravity, or we can select the direction of the global axis. I'm going to select the zeta axis, so the load will be minus because I want in the minus direction, in this direction. Value is minus 80. Of course, you have to select also the load pattern. We can use the previous one, that is force. We have to define again the load cases. We can use the previous one, with the scale factor of 1. And you can run the analysis. From the theory, I expected the rotation of this node equal to 0.3054 more or less, and the bending distribution, of course we have the distributed load, so the bending is not linear. .51 kilonewton meter. Again, if you want to see the results in terms of bending moment, you can push F8. You can see bending moment, that is this one. .51 more or less. You can see axial forces and the shear forces. Displacement are with F6. You can see that the rotation R with 2 is exactly the one that I expected, 0.00054. Ho alzato l'area. Sì. if you are able to use the displacement methods, you can validate the solution by using the displacement method. It's a really simple case because we have 4AE divided by L squared on the beam and the same on the column. Is a simple with the displacement method you will have this situation. With the substructure 0 you will have this one. With the substructure 1, the one rotated, you will have this that is 4A divided by L squared, the L of the beam, and this one is 4AE of the column divided by the L of the column. No, it's not square, sorry. And you can do an equilibrium between these three forces. This depends on the rotation. And you will obtain this value. Okay, two more questions. You can try to divide the finite elements into more elements by using edit option. In the edit option you can see edit lines and you can see divide frames. So we can divide into, for example, 5 each. You can see that now we have a lot of finite elements. So the solution will be more accurate. In this case it's more or less the same because it was accurate from the beginning. You can see that the bending moment is more or less the same. Maybe the displacement of the beam will be more accurate and the bending moment in the middle will be better. Another very useful option in SAP is that in SAP you can set the degree of freedom of the global model. So if you want to work only in this plane, in the x zeta plane, you can say to SAP to not consider the displacement out of plane. This is very useful for the buckling, because if you are interested only on the buckling mode on this plane, SAP will not consider buckling mode out of the plane. Of course, for our cases, it was not necessary to constrain the degree of freedom. This is simple to pass from a 6 degree of freedom beam to a 3 degree of freedom beam. In the plane of the blackboard, you have only 2 translation and 1 rotation. In the real 3D dimension, you will have 6 translation and 6 Everything was good with the frame?
Perché non consideriamo la lettura dei classi alti, cioè di dare classi sentenze?
Sì, e per validarlo con il metodo di spostamenti.
Se no, a mano come si fa le classi?
Devi considerare nodi, questi nodi rigidi, devi considerare nodi mobili considerando il contenuto della informazione.
Non lo so, magari quella pagina
Dopo aver rannato l'analisi. Spingere effetto.
Magari si fa applicarlo perché non aveva
I'm happy because all of you did this analysis, so we can do more complicated analysis because you are able to use software, so I'm happy. Last year was not so simple to perform a linear analysis, so great job, guys. Next step is to understand the behavior of the truss, of the bracing on a steel structus. Create a new file and save this one. is simple file, new model, and you will have again grid only model, blah blah blah. I want to create a new frame. I will show you. This is a classical steel structure with the bracing. You will see a lot of these structures if you became a designer of steel frame. Another type can be this one. This is the so-called bracing tower. For the seismic rule, you need bracing in your structures. You need a concrete core, or instead of using concrete walls or concrete core, you can use a bracing. Focus attention on these structures. These are columns and beams, and these elements are bracing. Normally the bracings are elements that works only in tension, and they have problem when they are compressed because of the buckling, the stability. But it's possible to perform analysis by consider only tension of the elements. Your software must do this, must consider only tension if you want to consider the real behavior of the bracing. So tension, okay. Compression is limited. Limited to the buckling forces, or no, we can just say no, no compression. This is a real behavior that you can observe in the real experimental activity or in the real behavior of your structures when the slenderness, that is the L divided by the radius, this value is the square of the inertia divided by the cross-sectional area. When the slenderness is greater than 200, the behavior of your bracing is only a tension behavior. I know that the steel material is more or less equal in the compression and in tension. But we have problem of slenderness and we have problem of buckling. Eurocode A, the seismic code of the Eurocode, says if you have this slenderness and if you are not able to use program that consider only tension, in the bracing, you have to model only tension element. So when the force is in this direction, these are going to the tension and these will go into the compression. So you have just to delete from your model these elements. But you have to create one model for the forces in this direction, other models for the forces in the other direction, because you will have to do this operation. So when you have a 200 combination of loads, it's not a very simple procedure. So it's better to understand how to create tension only element. Okay, I will show you how to do with SAT. We can create a frame by the same column are the H, the same cross section for all the columns. So I can do this one, sorry, I can do, so, see, columns are beam are the same IP, and the bracing, lacing or bracing are L profile 40 by 40 by 3. That means L that is 40, 40 and thickness of 3. Pay attention on the local axis and the principal axis. If this is the centroid and these are the direction X and Y direction, principal axes are rotated of 45 degrees. So this is column, 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 beam, 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 and L profile. I'm going to create a slender element, so this can be, for example, 2 meters. And this can be 3 meters. If you check with the properties, the slenderness of this is greater than 200.
Solo uno? No, dico solo su un piano.
Sì, sì. Only on the zeta and x direction. Another thing that you have to pay attention is everything is hinged. Previously we have created a continuous beam frame, a continuous frame. Now we have hinge everywhere. So two new tasks, hinge and tension only bracing. Okay. First of all, I'm going to create the grid. So the grid will be, again, I am not interested in the y direction. This can be 2 meters, 4 meters. This can be 3 meters and 6 meters. This is the grid. I gain 3 meters, 6 meters in the zeta direction, 2 meters, 4 meters in the x direction. We are going to create the material, define materials, new material, we can delete the other one. The same properties, of course, 210 gigapascal and 0.3 for the Poisson ratio. I'm not consider the elastoplastic behavior, so I'm not interested in these properties. And again, now I have to import the cross-section. So section properties, frame sections, import new property, HEB, and IP. I want to consider the real behavior of the beam and of the column, so I'm not modifying anything. So I want to see the real behavior by consider axial extensibility and shear deformation. That is the real behavior of again. So to create this tension only element in SAP, we have two streets. We can use cable elements, or we can create a beam element and say to SAP, this is a tension only element. Now I can show you the second one, the one with the frame elements. So we can import also the frame properties for the L. You can import or you can create. So we can also create to show you a different task. So instead of import new properties, we can add. You can see from the design of steel section, you have angle. In the option of SAP, you can also design your section. You can also design your section in AutoCAD and import into SAP. L section, and I'm going to put the dimension by hand, 40, 40, 3 and 3. Now for you it's very important to check the properties, because if you are using SAP or another software, maybe you will have difference on the round corner, because SAP take it straight. Maybe your software, I don't know, Strauss or Midas, gives you automatically a round corner. So this will change your properties in terms of second moment of area and cross-sectional area. But now this is not validation, so okay, for me they are okay. I know that the area now is 2, 3, 1, okay. But if you want to compare two software on software with the theoretical values, pay attention on this round corner that modify the area and the second moment of inertia, second moment of area. This is a L section 40 by 30, or if you prefer 40 by 40 by 3. Okay, now we have the cross sections. We can design our frame. First option, I'm going to design the frame by using only frame element. So everything is a frame element. Starting from the columns, now I'm designing everything continuous. Then I will apply the internal hinges. You can also design directly by internal hinges by using pinned. But I want to show you how to assign after the internal hinges. So, the columns, then the beams, lastly the trusses, the bracing. Okay, you can see the extrude visual. By using this display option, you can see also the name of the cross section. If you look at the object options and at the frame, by selecting section, you can see the name of the cross section. You can see also the number of the elements, of the finite elements, in both the frames and on the node. If you want to see the number of nodes, you can see in labels, joints labels, you will see the number of nodes. If you want to see physically the nodes in your design, you have to unselect invisible, and you will see the nodes. Okay, we can assign the restraint, external restraints. Now they are hinged, so not fixed. I'm going to fix only the translation. So only translation in 1, 2, and 3 direction. And I'm going to select the base joints. Okay, now internal hinges. We are going to select the frame on which we want to assign internal hinges. You can see from the assign frame that you have releases. Releases will release the degree of freedom associated with one of these elements. You can release the axial behavior, the shear behavior, or the bending moment. Now we are interested in the hinges, so we are going to release the bending moment. Pay attention on this start and end option, because here is really important the direction of the axis 1. Because if the axis 1 is from the left, from this point to this point, the start point will be this one, and the end point will be this one. To create a perfect hinge, I'm going to select both bending moment, but we need only one, but to be sure I'm going to select both. To create a perfect hinge, as you know, the perfect hinge have no bending moment. So I have to select as stiffness 0. What's mean? Cosa significa? What's mean this, sorry, releases? Releases are used to create semi-rigid joints. Semi-rigid joints give us the relation between the bending moment and the rotation. If you put a value, you have a relation that is depending on a value of stiffness. To be clear, when you have a real column with a real beam, maybe with a plane, maybe you have bolt, you have bolt and so on, charts, welding. This behavior cannot be a perfect hinge behavior. But in some cases, is accepted that you can your assumption can be that this behave like a perfect hinges. So you don't have bending moment on this connection. A diagram of bending moment, if you assume the perfect hinges, for example, if you have distributed load starting here from 0. But if you put a value of stiffness, as happen in the real life, this is not 0 but is related to the stiffness. This is a function of the stiffness. can be more clear. Continuous beam or continuous frame, you will have something like this. Then depends on the base, focus only attention on the beam. Perfect hinges. So this will be more greater than this one. Real life is in the middle. And this real life behavior depends on the stiffness of your connections. Now we are in this case, so we can put 0 as stiffness. Now bending moment can pass through the joint. This is the symbol that SAP uses for the releases. You can see releases in the display options, frame releases. And I'm going to assign releases on each beams. We don't need releases on this point, so for these 3 columns, we need releases only on the end. No, sorry, on the start. No, on the end, okay, because in the start we have the pin head. You can obtain the same result by put here fixed base and give the releases is the same, because you have fixed base, but then you put the hinges, so the behavior is equal to put an external hinges. This is our frame. Load case, we can assign some vertical and horizontal loads. For example, I don't know. Five kilonewton. And horizontally 10. To have a very great horizontal forces. Okay, again we have to define the load patterns. I'm going to create a unique case. We can decide to create a case for vertical and horizontal, or a unique case with both. We can create 2 different, okay, vertical, live load, modify, and horizontal, live load 0, add new. So now we have 2 different load patterns that are vertical forces and horizontal forces. Of course, I don't want to consider the self-weight, so I have to put 0 and 0. Pay attention when you combine different load combination, because if you put 1, if I'm going to put 1 on the self-weight multiplier on both, and then I'm going to combine, I'm going to consider the self-weight 2 times. So pay attention. So I have defined the load patterns, and I have to create now the joint loads. Joint loads, forces, starting from the horizontal, I have 10 kilonewton on these nodes in the x direction. And I have in the vertical one 5 kilonewton. If you want to display the loads, you have the display option, display. You have show load assignment, joints. Here you can select horizontal or vertical. Vertical and horizontal. We can define the load cases. I'm going to delete everything. Add new load cases. Okay, now starting with the static linear analysis. Pay attention to add both horizontal and vertical in the same load cases. This is a linear static analysis. And we can run. Now I performed an analysis by considering the trusses, the bracing working both in compression and in tension. That is not correct because I have a slender element. We can look at the displacement. And I can say displacement 3.65. So if I design this frame by consider both works in compression and tension, I'm wrong, and I give to the committant, I will give the displacement of my frame is 3.6 displacement. I can say displacement wrong 3.65. But as I told you, this is not the truth. Look at the axial forces distribution, F8, axial. You can see that we have tension and compression. We have the maximum tension value on the bracing is 17.96, so 18. Maximum tension. 15 kilonewton. And if you look at the columns, the maximum value of the compression on the columns is 12.6 kilonewton. This is the wrong. I say 12.6. But this is not the real behavior of your frame, because this must go in buckling. So we can see what's happened with the correct only tension element. So we have a different option. I'm going to use this one. I'm going to select the bracing, assign frame. You can see that you have tension compression limits. So assign frame tension compression limits. You can say the compression can be limited to the value of buckling, for example, or 0.5 the value of buckling. In my case, I don't want any compression in the bracing, so I'm going to put 0 and not be compressed. So compression limit equal to 0. Now the really important thing is this one. SAP must understand that these elements are in compression or not. So the analysis cannot be a simple linear analysis, because SAP needs 2 steps. Needs the 4 steps to understand which elements are going in compression, and the second step to exclude the compressed elements and to perform a new analysis. So if you return back to define load cases, I'm not interested in the static linear, but in the static non-linear. Now I'm not interested in the P delta effect or large displacement effect. These are the effects that I told you before at the beginning of the lecture, when you want to consider the geometrical stiffness into the analysis. If you select static nonlinear with known, remain a linear static analysis, but a stepped analysis. So SAP perform a first linear static analysis and understand which elements are going in compression. Then create a new matrix with the only tension elements and perform again the linear analysis. This analysis will be slower, but with these very small elements is still fast. Okay, first of all, I want to see the displacement. See what's happened. The displacement is double. The real displacement of your frame is 7.5. That means, okay, this is not a real case, but in the real life, maybe you have a limit of displacement because here there is something. Maybe with the 3 you are okay, but your real displacement is 7, and maybe you can have problem of collision or some others. Pay also attention, when you have great displacement, you have great flexibility and you have great second order effects. So great bending moment and so on your frame. We will see. We are going to see the axial forces. you can see that these elements, previously I am very happy because the tension was only 18, now is 36. So it's double. And look at the maximum compression on the column is 50. It's not the same column because in the other analysis was this one, but maybe more or less they have the same buckling length, so the verification checks are the same. So previously was the maximum 12, now we have 50. I expected to obtain the same results by performing the previous analysis by deleting the compressed element by hand. So I'm going to remove the limit. Of course, if you leave the limits of compression and you perform a linear static analysis and not a nonlinear, you will have the same result. So if I put here linear with the compression only elements, you can see that the displacement remains 3.6 because I need a nonlinear analysis. If I remove by hand the compressed elements, I obtain the same results in terms of both displacement and internal forces. So this is why the Eurocode 8 gives you this recommendation to remove by hand the compressed elements. Okay, last thing you can do by yourself to try to model this element by using cables instead of frames. You can create cable, put here an area, and you can design a cable instead of a frame. So when you have draw, you select cable, cable are elements that are able to resist only tension for their definition. Siete riusciti a fare queste analisi? Quando rilancia torna alla versione iniziale.
Therefore, the Americans those classes from 1668 are the problem. People with the problem that you get.
Because last year, during those hours, he did like a project. Yeah, at the time, yeah, but he did it so. That's why I'm calling somebody else. People in last time. Just find someone else. That's it. Just
Missione dei risultati. Sì, un po' là.
Okay, the lecture for me is okay. If you have a question, we can I can pass through the PC and look for some question. See you next time.